Hello, my name's Greg Johnston. I'm a senior in software, and we're a ground penetrating radar manufacturer from Canada. I'm fairly confident when I say that the #1 application for GPR worldwide is utility locating. To me, the simple reason for this is its ability to detect both metallic and non-metallic objects. In the utility world, this is things like plastic and concrete pipes. Seeing non-metallic objects complements the main locating method for utilities, which is EM induction, which is dependent on some sort of metal content in or near the utility. Now, because you are attending a webinar called How to Get the Most Out of Your GPR Utility Data, I'm going to assume that you've had some sort of GPR training, either a formal course offered by a GPR manufacturer, or at least an on-the-job training course by your boss or one of your coworkers. Okay, a typical GPR training course for utility locators, let's call it GPR 101, goes something like this. Lesson 1. GPR is a technology that uses radio waves to image objects in the subsurface. Lesson 2. Hyperbolas are the GPR response to an object in the subsurface. Lesson 3. Hyperbolas form as the GPR passes over top of an object. Here's an animation that shows this concept. Lesson 4. The actual location of the object is at the top of the hyperbola. After you find an object, the question utility locators want answered is whether the object is a utility or not. So that leads to lesson 5. If you collect a series of parallel GPR lines and find hyperbolas at similar depths and of similar character that line up in a straight line, the subsurface object is linear, and there's a very good chance that it's a utility. Let's face it, when hyperbolas are strong, isolated, and linear, utility locating with GPR can be pretty easy, as this example shows. 5 parallel lines, 5 very good responses, all look very similar. We mark their location on the ground, they all line up. Pretty easy. But GPR does have limitations. It's not a miracle tool that solves all the problems of a utility locator. I think we all know that at times, the capabilities of GPR are oversold, and there's an expectation gap or a knowledge gap that leads to disappointment for some users. To attempt to remedy that today, I'd like to dive a bit deeper into some of the fundamentals of GPR and equip you with a few more tools to get the most out of the GPR data you collect and understand it a bit better. This is my agenda. I'm going to go through a bit of theory at first, and then we'll get to the meat of this webinar, which would be concrete things that you can do to get more out of your GPR data. Okay, let's go back to my opening animation and ask a question. Why does the GPR pulse reflect from the concrete sewer pipe? GPR waves reflect when there's a contrast of materials, specifically a contrast in a material property called the dielectric permittivity. If you are interested, you can look up the details of this property. But in my mind, the details of the property or even the name is not that important to know. It's only important to understand that a change in this property is what causes GPR energy to reflect. We understand this concept intuitively because every day we look at objects and know that the reason we see them is because they contrast with the air around us. The light reflects off them into our eyes. GPR waves do the same thing in the subsurface. Here's another animation that shows the concept of what happens when a GPR pulse is sent into the subsurface and reflects from a boundary between 2 contrasting layers. It is interesting to watch this animation for several reasons. One reason is the complex shape of the reflection, even from a relatively simple boundary. Imagine how complex it can get if the surface was rougher and the layers were full of objects that caused other reflections. The other reason this animation is interesting to watch is to see that not all the GPR energy that hits the boundary reflects back to the surface. Some of it transmits through the boundary and keeps traveling downward. If you watch it a few times, you will even see that the energy that travels through the boundary acts like the boundary is not even there. If you watch it a few more times, you can estimate how much of the GPR energy reflects versus transmits through. If the GPR energy just before the interface is 100%, you can see that about 30% of the energy reflects and 70% transmits through. Again, we are familiar with this phenomenon. Anytime you look out a window at night, you are experiencing energy transmitting and reflecting at the same time. In this example, we can see the lights of the city outside, but we can also see the reflection of the woman in the glass. Light rays are reflecting and transmitting at the same time. GPR signals do exactly the same thing. Another question that's very important for the use of GPR is, what controls how much energy reflects? The reason this is important for GPR is because we know, or at least we should know, that the more energy that reflects back to the surface and is detected by the GPR receiver on the surface, the better chance we have of seeing that buried object. So again, what controls how much energy will reflect? The answer is the magnitude of the contrast of the materials. Let's look at the dielectric permittivity values of common materials we will encounter while utility locating. Dielectric permittivity uses the capital letter K for short. So you will sometimes hear me call it K so I don't get so tongue-tied trying to say dielectric permittivity. Just think of it as K for contrast and don't think too much about the spelling. On the left are K values of typical materials that utilities are buried in. On the right are K values of typical materials that utilities are made of or contain. Notice that concrete is on both lists because sometimes it is a host material and sometimes it is what the target's made of. You can see here that except for metal on the bottom right, most materials have a dielectric permittivity between 1 and 80. The two extreme materials in this range are air at 1 and water at 80. Everything else is in between. PVC is 4. Dry sand is 5. Rock is 6. Silty soil is 30. And clay soil is 40. So the amount of GPR energy that reflects from an object depends on the contrast between the K of the object and the K of the surrounding soil. The bigger the contrast, the more GPR energy that reflects. That is called the reflectivity. And here's the formula for calculating it. But let's look at some examples related to utilities. Let's start with an easy one. Water saturated sand with a K of 25 going to metal. For example, a metal cable buried in the subsurface. Metal has an infinite dielectric permittivity. So when you do the math from the formula, it has a 100% reflection coefficient or reflectivity. This means that 100% of the GPR energy that hits a metal object reflects, and none of the energy transmits through the metal. This is the reason why metal objects are the easiest objects to detect with GPR, as this example shows. Now, let's talk about GPR detecting non-metallic utilities, such as PVC and concrete pipes. Say we have a concrete pipe with a K of 4.5 buried in a dry sand with a K of 5. Even before we do the math, you can see that there's not much contrast, so we can predict that the reflectivity is going to be small. Sure enough, when you do the math from the formula on the last slide, the reflectivity in that situation is 2%. Only 2% of the GPR energy that hits the concrete pipe reflects back to the surface, and 98% of the energy transmits through. A PVC pipe in dry sand is not much better. A PVC pipe with a K of 4 buried in a dry sand with a K of 5 gives us a reflectivity of 6%. With such low reflectivity, how does GPR ever find non-metallic utilities? The assumption that most people make is that GPR detects the plastic, PVC, concrete, fiberglass, or whatever the pipe is made of. Well, the reflection from a non-metallic pipe does not only come from the pipe itself. It comes from the material inside the pipe. In fact, most of it comes from the material inside the pipe. That is where the contrast comes from. So with that knowledge, let's look at the numbers again. Let's say that there's air inside our concrete or our PVC pipe. Air has a K of 1. If the dry sand has a K of 5, that's the soil around it, and the air inside the pipe has a K of 1, this gives us a reflectivity of 38%. Way more energy reflecting back to the GPR receiver on the surface. Way more detectable. Here you see the theory and the reality. One hyperbola has a significantly stronger response than the other. Since they're at the same depth in the same soil, one explanation for the difference in the reflectivity is the target material. One interpretation may be that it's a metal target on the left and a non-metal target on the right. Okay, let's add water to that dry sand and make it wet sand. So now our air-filled non-metallic pipe is surrounded by wet sand. What does that do to the amount of energy that reflects from the pipe? The contrast between wet sand and air is larger than between dry sand and air. So more energy reflects in the wet sand situation. 66% versus 38% in the dry sand situation. That means that a non-metallic air-filled pipe is easier to detect in a wet sand than a dry sand. How many of you have heard somebody say, I could not do the GPR survey because it rained? Or, the GPR survey was not successful because it rained. Yeah, me too. But as these calculations show, when you're looking for an air-filled utility, a water-saturated soil can be very helpful. Keep in mind that the only change in this scenario is that we change dry sand to wet sand. Let's talk about this for a minute. So what's the difference between dry soil and wet soil? This is not a trick question, it's water. Water has a very high dielectric permittivity, 80, much higher than dry sand or almost any dry material like soil. When you replace the air in the pores between the grains, which has a very low K of 1, with water, which has a K of 80, even though the pore space is a small percentage of the total volume, it increases the K for the soil. In fact, the presence of water in a soil has the largest effect on the K value of that soil. Notice the range of values. Dry sand is 5. Wet sand is 25. If you go to a swampy mixture like quicksand, you can even get K values that are more than 50. Simply put, the more pore space with water in it, the higher the K value for that soil. And that's a great situation when you're looking for air-filled non-metallic pipes. Let's talk about the opposite situation, a water-filled non-metallic pipe. Not surprising, it's the exact opposite. There is more contrast between dry sand with a K of 5 and water, the water in the pipe with a K of 80, than there is between a wet sand with a K of 25 and the water in the pipe with a K of 80. So here are the numbers. 60% reflectivity in the dry sand situation, 28% reflectivity in the wet sand situation. It is going to be easier to find a water-filled non-metallic pipe in a dry soil than it will be in a wet soil. Here is everything we just talked about on one slide. In terms of reflectivity, Metal objects are always the best. Next is gas-filled pipes in wet soil. Then comes water-filled pipes in dry soil. The hardest objects to find: water-filled pipes in a wet soil and gas-filled pipes in a dry soil. The reason? Less contrast, so less reflectivity. Here's an example of what can happen. The contrast with the utility was high enough that even though the GPR signal was very weak at depth, a high percentage reflected from the concrete asbestos pipe, making it just barely detectable with the GPR. And this is a real object. They ended up digging it up after we found it. What I'd like you to understand from this whole discussion is that when you look at a GPR line, you should be thinking that it's an image showing the contrasts between layers and objects. Some are large contrasts that produce strong reflections. Here's a strong hyperbola that's weaker even though it's deeper. Here's a weaker hyperbola that's shallower than this deeper one. There's information in these observations that will help you interpret your GPR data better. When we zoom in to this area, we can see a number of weak hyperbolas. I want to emphasize that those are real objects in the subsurface. I've heard people say phantom hyperbolas. I don't know what those are, but I don't believe that phantom hyperbolas exist. A hyperbola, whether it's strong or weak, is a reflection from an object. The strength of the hyperbola is due to the contrast between that object and the surrounding soil, as we've been discussing. In this case, because I see strong hyperbolas down deeper, I might ignore these weaker hyperbolas and interpret them as being from an object that has a similar K value as the soil, maybe rocks, clumps of dirt, something along those lines. But if I was looking for a utility that might be subtle, a fiber optic line, a non-metallic water line in a wet soil, or a non-metallic gas line in a dry soil, I should take a second look at these hyperbolas and collect more data to see if I see them again on parallel lines. If so, this would mean that they form linear objects, which usually indicates a utility. Okay, new topic. I know that you all know this because it's intuitive. GPR signals get weaker as they travel deeper into the subsurface. But let's just make sure we understand what's really happening. Reflections get weaker with depth. There are actually several reasons for this, but the dominant reason, and the one I want to talk about today, is called signal attenuation. The depth that GPR signals travel into the subsurface before they are completely attenuated or absorbed is controlled by the electrical conductivity of the soil. We know this more commonly as clay is bad for GPR, but the underlying cause for people to make that statement is that clay-rich soils generally have a high electrical conductivity. So here's an animation that shows what happens to the GPR signal as it travels in materials with different electrical conductivities. On the left, low electrical conductivity results in slower attenuation of the GPR signal and a lot of reflected energy making it back to the surface. We know that we can only detect an object in the subsurface with GPR if the energy reflects and makes it back to the GPR receiver on the surface before it gets completely attenuated. In the middle is a material with higher electrical conductivity. The GPR signal is attenuating, but a little bit of the signal makes it back to the surface. We would see this object, but it would be weak. You can just see a little bit of energy making it back to the surface. On the right is unfortunately what many soils are like. They have high electrical conductivity and absorb the GPR signal quickly. In this case, the GPR energy makes it down to the object and reflects, but it's completely absorbed before it makes it back to the surface. This object is invisible to GPR. Most GPR practitioners have been in this situation, trying to explain to the client why the GPR did not find the object they're looking for. The culprit is often soils with high electrical conductivity. The soil may naturally have high electrical conductivity, such as clay soils, but materials with high electrical conductivity can also be introduced to the soil. This sometimes happens when they add fill to an area to even out a surface. The native soil in the area may be great for GPR because it has low attenuation and allows the GPR signal to travel deep. But then you walk across a filled area and the penetration decreases because it has higher attenuation. I've also seen the opposite situation. Bad native soil, and the fill that was added is actually better for GPR penetration. This goes along with one of my messages today, which is GPR can be hard, but don't give up too quickly. Okay, so now that I've got the GPR reflectivity and attenuation out of the way, let's talk about a few concrete ways that you can get more out of your GPR utility data. Look at the bottom of this GPR line. What is the signal that looks like a snowstorm or an old school TV station not coming in properly? Some of you will know that this is background radio frequency noise. It's important to remember that a GPR receiver does not only record GPR signals, it records radio signals. So it records the GPR signals and any other radio frequencies in its bandwidth. To us, these other radio frequencies are unwanted, so they're called radio frequency or RF noise. And if the depth setting for your GPR line is deep enough, you should always see RF noise at the bottom of the GPR line. RF noise comes from many different sources: radio stations, TV stations, walkie-talkies, cell phones, military communications. The sun emits radio waves. The universe emits radio waves. The surface of the earth is immersed in radio waves at all times. So you will always see RF noise in your GPR data, even if the antenna is shielded. Now keep in mind that the RF noise is usually about 1,000 times weaker than the GPR signals we are transmitting. So you don't see RF noise until the GPR signals attenuate down to the noise level. But here's something else good to know about the noise in a GPR line. It is masking perfectly good GPR data from down deeper. For example, here is a GPR line on the left. On the right is a plot of the GPR signal strength. The GPR starts to record data just before the GPR transmitter fires. Strong, shallow reflections arrive at the receiver. These signals get weaker and weaker as they travel deeper into the subsurface and are attenuated. Finally, the GPR signals get to zero amplitude. If we look at the GPR line on the left, we see that the GPR reflections stop at about the red line, this red dashed line. This is called the depth of penetration. Wait a second. Why is this the depth of penetration if GPR signals are still present below that line? Because I forgot to include the background RF noise in the plot. When we plot that, this is what we get. So the depth of penetration with GPR is not when the GPR signals attenuate to zero. The depth of penetration is the depth at which the GPR signals, shown here in blue, attenuate down to the same level as the background noise floor, shown in yellow. In fact, external random RF noise is one of the main factors that limits GPR penetration depth. If you think about it, there's GPR signal buried in the noise. If we could eliminate or at least lower the background noise level, we would see GPR signals from deeper utilities. Now I want you to pay attention to my fancy animation that shows this concept. Notice how when the noise floor drops, we can see a deeper hyperbola in the data that we couldn't before. Stated another way, the depth of penetration will increase if we can decrease the noise floor. So how do we do this? By stacking or averaging the data. Some of you have probably heard about stacking. The ability to stack GPR data has been a part of all our GPR systems since the 1980s, so it's not new. But let's talk about what stacking can do for us. Stacking means that rather than just recording the signal every time the GPR transmitter fires, like this, fires, what we collect, what we save. We allow the transmitter to fire multiple times at one location. We then average the traces and we only record the average trace. So if we stack 2 times, we fire the transmitter once, we save the trace. We fire the transmitter a second time, save that trace. Then we average the 2 traces and we record the average of those 2 traces. If we stack 4 times, we fire the transmitter 4 times, save all 4 traces, then we record the average of those 4 traces. Same with 8 stacks. The key point here is that stacking traces multiple times and saving the average trace lowers the amount of noise, shown here as red signal, in the average trace. The more you stack GPR traces, the lower the noise, the better the GPR signal, and the deeper the depth of penetration. Here's another way of showing this concept, perhaps a better way, because it shows what actually happens when you're collecting the GPR data. Notice that the average trace of the 4 traces collected has less noise, again shown as red signal in this example. Since there are GPR signals buried below the noise, this means that if we can decrease the noise, we can see those weaker, deeper, real GPR reflectors. Here's the same idea in a table. This number of stacks that were shown here on the left are the number of stacks available in sensors and software GPR systems. Stacking data 100 times reduces the noise level 10 times to 10% of the noise at one stack. Stacking the data 10,000 times reduces the noise 100 times to 1% of the noise at one stack. The effect of stacking is shown in this animation of a GPR line. In this example, the target is a flat metal plate buried 3 meters or 10 feet in the ground at the University of Arizona. Now, some of you know that Arizona soil is generally not very good for deep GPR surveys. It tends to be very electrically conductive, which, as we know, attenuates GPR signals before they can travel very deep. But this example shows the power of stacking GPR data. At one stack, the depth of penetration is about 1.8 meters. But you'll see that by about 512 stacks, the depth of penetration is increased to about 3 meters, and we start to see the metal plate. Beyond that, by 1,024 or 2,048 stacks, we have a good image of the metal plate and lots of confidence that this is a real subsurface object. By stacking, the depth of penetration is increased more than 50%, which is significant if you're trying to detect every buried utility you can. Here's another example showing the same GPR line collected with 256 stacks on the left and 65,536 stacks on the right. Notice how the background noise is greatly reduced by stacking the data. At 256 stacks, we can see a hint of 3 hyperbolas that we would be gutsy and probably very uncomfortable to say are utilities. But at a higher number of stacks, the hyperbolas are so strong and obvious, we'd have no problem making that interpretation. So to get the most out of your GPR utility data, consider stacking more. Sensors and software systems make that easy. All you have to do is walk slower. That gives the GPR system the time it needs to stack the data more and increase the depth of penetration. Some of you may be familiar with the dark blue DynaQ bar plotted under GPR lines. The DynaQ bar is a color indication of how much the GPR trace above it has been stacked. Okay, now let's talk about gaining your GPR data. For most GPR operators, this is well known, but I mention it because I often see utility locators not spending the time necessary to gain their GPR data properly, and that can result in missing utilities in the data. As we mentioned, GPR signals get weaker with depth because of the attenuation or the absorption of the signal by the soil. The signals at the top of the GPR cross-section can be thousands of times stronger than the signals at the bottom. This means that GPR signals usually need to be gained or amplified, especially the weaker signals at depth. The gain we apply to the data is actually a ramp, so there's more amplification applied to the deeper, weaker signals than the shallower, stronger signals. After we apply gain, you can see that the deeper signals are stronger and more visible. So let's look at an example. Here you can see that while the image on the left looks like it might be okay, because we can see a hyperbola that could be a utility, when we apply more gain, we find that there's a second target that is deeper and weaker that we almost missed. It's important to realize that there is no perfect gain. If there was, we would not have an adjustable gain setting. We would just apply the perfect gain. The GPR signal attenuates at different rates in different soils at different locations. So gain is something that constantly gets adjusted throughout a GPR survey. A simple way of making sure that you've applied enough gain is that you should be able to see the random snowy signals from external radio sources at the bottom of the section. Once you can see that noise, you've usually applied enough gain. Another way to see more in your utility data is by applying a filter called a background subtraction filter. GPR does not just image the objects you're interested in seeing. It shows all the contrast changes in the ground. And some of those changes are not even objects at all. They're soil boundaries and horizontal banding. As a utility locator, you are rarely going to be interested in soil boundaries. They just clutter up the image and can mask the hyperbolas from the utilities that you do want to see. As this example shows, the filter removes flat-lying reflectors in the data. These are things that utility locators are not interested in. And the filter enhances the hyperbolas that you are interested in. So we see this hyperbola, which was very difficult to see before. We see it more clearly after we apply the filter. Okay, in this example, I'm showing a multi-level filter going from 0, which is no filter, to 5, which is the strongest filter. What you see is the higher the filter value, the more flat-lying reflectors it removes from the data. This helps emphasize a few hyperbolas that are masked by the flat-lying reflectors. My two favorite examples in this data are confirmation that the hyperbola at 22 meters is a real target, and the trench at 32 meters. You can see, get a hint of this trench, but once you apply more of a filter, you can see the two sides of it. And if you look closely, you can even see what may be the object, the hyperbola from the object that's buried in the trench. Okay, here's a common story of utility locating with GPR occurs at complex sites with many utilities. I call it the chasing hyperbolas technique. Here's a play-by-play of the data collection. Oh, I see a nice hyperbola here. It looks like the utility is going in this direction. Wait, why don't I see another hyperbola where I was expecting? Oh, here's another one. Why is it deeper than the first one? And on it goes. The locator spends all their time putting marks on the ground and trying to connect the dots and make sense of the site. Frustrating and often unsuccessful. The only way to sort out the utilities in a complex area is to collect data in a grid. Most GPR systems allow data to be collected as grid scans. In this example, a 30 by 36 foot grid was collected with lines every 2 feet. You can see that lines were collected in both the X and Y directions. After we collect the grid, it can be processed into a series of depth slices, each slice usually a few inches thick. It's like peeling the layers off the top to peer deeper and deeper into the subsurface. Depth slices allow us to see the orientation and spatial relationship of multiple targets. In this example, the red responses are objects with high reflectivity, reasonably interpreted as utilities. Slicing through the data reveals the complexity of the utilities on this site. You can watch this animation several times and still see new utilities. So depth slices can really assist in interpreting GPR data in a complex area. I hope you see that collecting GPR data in grids is powerful. If you use grids in your day-to-day GPR data collection, I congratulate you on your enlightenment. But let me tell you the complaints that we hear a lot. Grids are time-consuming to set up. Grids are complicated to set up. My area of interest is not rectangular in shape. I don't want to break up my area into lots of smaller grids to cover it all. My survey area is too cluttered to set up a grid. So let's go back to the fundamentals. Why do we need grids? Well, really, the reason we need grids is because we need to know the XY position of every GPR trace we collected. But there's another way that I can get an accurate position of every GPR trace. And those of you will say GPS. Absolutely. If your GPR has an accurate GPS, but what I mean by that is less than 1 meter of accuracy, you are working in an open area with lots of sky visible, another way to generate a depth slice is to collect a pseudo grid and use the GPS for positioning the GPR data. Basically, cover the area by walking back and forth with the GPR system to collect closely spaced lines, ideally the width of your GPR system. The data is then processed into depth slices on a PC. Here we see that somebody wandered back and forth around this field with zigzags and various line spacings. Here's the depth slice animation generated from the pseudo grid data. Rapidly slicing through the data reveals that there are 3 linear utilities that are the main features in this area. 2 of them are here. They're actually at different depths. You see one now, and now you see the deeper one now. And then over here, there appears to be one linear one running through there. So the other strong responses just are point targets. So as you can see, and maybe hear in my voice, I'm a big fan of depth slices. Whether they're generated from grid scans or pseudo grid scans, I love them. But there is a big but. Depth slices are powerful, but it is important to remember that depth slices are maps of target reflectivity at different depths in the subsurface. If hyperbolas are weak because they're from a non-metallic utility, have little contrast with the soil, or because the utility is close to the maximum depth of GPR penetration in the area, you may not see a linear target in the depth slice. These are the utilities that are often missed in GPR data. Increasing gain can help, but not always. Now, can you recognize this as a utility? This feature in here? If so, how confident would you be? So let's talk about increasing our confidence that a weak hyperbola is actually a utility. Here's an example of weak hyperbolas that are clearly visible to your eye, but are too weak to appear as a strong linear target in a depth slice. So how do we augment the depth slices to show these weaker hyperbolas? We do that by adding point interpretations to them. We take advantage of your eye's ability to see weak hyperbolas and we add points to them. In this example, I've added pink dots to the tops of the weak hyperbolas. If we were interpreting this depth slice, we would probably wonder if this faintly weak yellow area that's kind of linear is actually a utility. However, when we display the depth slice with point interpretations added, we see that this is a linear object, and our confidence that it's a utility has just increased dramatically. Once we plot the interpretation in a map view, we can see that many of the other hyperbolas we added interpretations to turn out to be just point objects in the ground. So adding interpretations is easily done right in the field by touching the screen at the top of the hyperbola as you're collecting data. You can also add point interpretations after you've finished collecting the line and are reviewing it on the display unit. Our LMX200 system has a screen we call SplitView that displays the GPR cross-section and the map view at the same time. This shows the relationship of all the interpretations you've added to the data. SplitView allows you to get instant confirmation that the interpretations you're adding to the cross-section is a linear feature in map view. Watch what happens as I add a point to the top of the hyperbola. If I add a point here, it appears in my map view over here. And once we see hyperbolas lining up like this, it increases our target confidence. SplitView also gives you an indication of where you may have missed adding an interpretation. In this example, we have 5 dots that all line up, and we have another one that looks like it's missing. Odds are you missed it. So you can scroll back through the GPR line, find where the hyperbola should be, and take a second look at it. I'm often asked, what do I do when there are lots of hyperbolas in my data? How do I sort them all out? Well, as I've shown, start with depth slices. So here's an example where somebody walked 7 kilometers or 4 miles back and forth across the survey site. Here's the depth slice animation, slicing down 10 centimeters at a time. You can see several utilities come and go at different depths. Here is one of the key depth slices showing several utilities. Just to ensure that they found everything they could, they went through the GPR lines and added interpretations to all the hyperbolas in the data. They had different colored dots depending on the depth and character of the hyperbola. They used blue for hyperbolas that they thought were utilities. They used green for ringing hyperbolas that they thought were just pieces of metal debris. And they used brown dots for hyperbolas that they thought were caused by tree roots because there were lots of trees in the area. When the depth slice and colored interpretations were plotted together, this is what they got. They found a few linear targets that they did not see in the depth slices. They also found that many of the hyperbolas that they thought would be utilities turned out to be just point objects buried in the survey area. They also found that there were lots of metal debris scattered around the site in no particular pattern. Those are the green dots. The last way to get the most out of your GPR utility data is perseverance. Make many passes before giving up. You just might find a patch of soil that is better for GPR and allow you to get a glimpse of the elusive utility you're looking for. In this example, here are 2 lines that were collected less than 2 feet apart, and one clearly shows the utility and the other doesn't. So in summary, we've talked about target reflectivity and attenuation, and I discussed that so that you have a better idea of knowing what you're looking for in your data depending on the target. I also talked about getting the most out of your data, doing things like stacking as much as you can. Make sure you spend the time getting a good gain. You don't want to miss a target in your data that's there. It's there, you just missed it. Use the filter, and ideally use a multi-level filter to enhance hyperbolas from utilities. Collect grids or pseudo grids at large and complex sites to generate depth slices. And finally, because we don't always see linear features from weak hyperbolas, we can add point interpretations to augment those depth slices and make a better final product. And that will improve our interpretations and give a better product for our customer. So that is my presentation for today.